Our topic for today is about Yagi Antenna. The full name for the antenna is Yagi Antenna. The Yagi Antenna derives its name from two Japanese inventors, Hidetsugu Yagi and Shintaro Uda. The RF antenna design concept, its use has grown rapidly to the stage where today a television antenna is synonymous with an RF antenna having a central boom with lots of elements attached. The design for Yagi antenna appears to have been initially developed not by Yagi, who was a student, but his colleague Professor Shintaro Uda. However, all the original papers were all in Japanese, and accordingly the design was not publicized outside Japan. Yagi and Uda published their first report on the wave projector directional antenna. So this is Dr. Shintaro Uda of Tohoku Imperial University, Sendai, Japan, with the collaboration of Hidetsugu Yagi, also of Tohoku Imperial University. So this is the picture of Yagi and his Yagi antenna. Yagi published the first English language reference on the antenna in 1928 survey article on shortwave research in Japan, and it came to be associated with his name. However, Yagi always acknowledged Uda's principal contribution to the design, and the proper name for the antenna is Yagi Uda antenna or array. So this is the picture of late World War II Me-100 Night Fighter, features the prominent Yagi arrays of its FUG-220 radar. The Yagi was first used during World War II for airborne radar sets because of its simplicity and directionality. Deep sight, it's being invented in Japan. Many Japanese radar engineers were unaware of the design until very late in the war. Partly due to rivalry between the Army and Navy, the Japanese military authorities first became aware of this technology after the Battle of Singapore, when they captured the notes a British radar technician that mentioned in Yagi antenna. Yagi Uda antenna. A Yagi is simple to construct. Yagi antenna have high gain on the high frequency, very high frequency, and ultra high frequency bands. Operation from 3 MHz to 3 GHz. So this is the drawing of very high frequency television antenna from 1954, used for analog channels 2 to 4 MHz, 47 to 68 MHz. It has 5 elements, 3 directors to left, 1 reflector to right, and the driven element, which is a folded dipole to match a 300 ohms impedance of the twin lead feed line. Its beam direction is off the support boom to the left. So this is the picture of ultra high frequency Yagi television antenna. A modern high gain UHF Yagi television. It has 17 directors and 4 reflectors shaped as a corner reflector. 3-element Yagi antenna, used for long distance skywave communication in the shortwave bands by an amateur radio station. The longer reflector element, the driven element center, and the shorter director each have so-called trap inserted along their conductors on each side, allowing the antenna to be used at 2 different frequency bands. So 2 elements Yagi shown in the 2 configurations. Letter A and B are almost equal in gain and direction. Letter A, the director is about 5% shorter than the driven element. In letter B, the reflector is about 5% longer than the dry-bend element. Two-element Yagi using a single parasitic element. At letter A, the parasitic element acts as the director and letter B as a reflector. The arrows show the direction in which maximum radiation takes place. Some major antennas and their discovery/fabrication dates. Yagi Antenna, 1920s. Horn Antenna, 1939. Antenna arrays, 1940s. Parabolic reflector, late 1940s. Patch antenna, 1970s. Planar invented F antenna or PIFA, 1980s. Yagi Antenna basics. Dry-bend element is excited directly via feed line. All other elements excited parasitically. Lengths and diameters of elements plus their spacing determine antenna behavior. Dry-bend element size and diameter has little effect on forward gain but significant in effect on input impedance and backward gain. Reflector spacing and size has little effect on forward gain but effect on backward gain as well as the input impedance. Directors, the most critical part of a Yagi design, control front and backward gain and input impedance. So there are three types of elements within a Yagi antenna. We have dry-bend element, reflector, and the director. Dry-bend element. The dry-bend element is the Yagi antenna element to which power is applied. It is normally a half-wave dipole or often a folded dipole. The reflector element is made to be about 5% longer than the dry-bend element. The Yagi antenna will generally only have one reflector. This is behind the main dry-bend element. Example, the side away from the direction of maximum sensitivity. Director. The director or directors are made to be shorter than the dry-bend element. There may be one or more reflectors in Yagi antenna. The director or directors are placed in front of the dry-bend element. In the direction of maximum sensitivity, typically, each director will add around 1 decibels of gain in the forward direction, although this level reduces as the number of director increases. Antenna has gain allowing lower strength signals to be received. The Yagi antenna has directivity enabling interference levels to be minimized. Straightforward construction. The Yagi antenna allows all constructional elements to be made from rods, simplifying construction. The construction enables the antenna to be mounted easily on vertical and other poles with standard mechanical fixing. Disadvantage. For high gain levels, the antenna becomes very long. Gain limited to around 20 decibels or so for single antenna. How does a Yagi antenna generate gain? Signals arriving at A strikes all three elements and generates a current on each element. The signal are radiated by the director and reflector and arrive the dry-bend element in phase with one another. The signals reinforce each other and make the incoming signal much stronger coming from direction A. When the signal comes from direction B and C, except that they arrive at the dry-bend element out of phase with one another, which simply means they cancel each other out, significantly reducing signal from direction B and C. More elements is equal to greater than gain. As you add more elements, you enter the harsh word of diminishing gain for additional added elements. So, the approximate Yagi antenna gain levels. We have 2 elements and the approximate decibel gain are 5. 3 elements 7 decibel gain and 4 elements 9 decibel gain. 6 elements have 10.5 decibel gain, 8 has 12.5 decibel gain, 15.5 decibel gain. Multi-element Yagis is equal to gain and power. Here is the azimuth pattern for 6 elements 20-meter Yagi on 60-foot long boom, mounted 60 feet over ground. At A, the azimuth pattern angle is shown compared to a dipole at the height. Peak gain of the Yagi is 16.04 dBi, or just over 8 decibels compared to the dipole. At B, the elevation pattern for the same 2 antennas is shown. Note that the peak elevation pattern of the Yagi is compressed slightly lower compared to the dipole, even though they are both at the same height over ground. Yagi matching techniques. Element spacing. There is a level of impedance variation that can be provided by altering the spacing between the elements. However, it is not possible to bring the feed impedance back up to 50 ohms needed for the most feed applications. Balloon. A balloon is an impedance matching transformer and can be used to match a great variety of impedance ratios, provided the impedance is known when the balloon is designed. Delta match. This method of Yagi impedance matching involves fanning out the feed connection to the driven element. Folded dipole. One method which can effectively be implemented to increase the feed impedance is to use a folder dipole. In its basic form, it raises the impedance fourfold. Although by changing various parameters, it is possible to raise the impedance by different factors. Gamma match. The gamma match solution to Yagi matching involves connecting the out of the coax braid to the center of the driven element. The center via a capacitor to a point away from the center, dependent upon the impedance increase required. So that's it. Thank you for watching.